Alright, so now we're going to take a look at section 15.4. And 15.4 deals with an application of double integrals. So in this section, we're actually going to be looking at one specific application of the double integral. We're going to be taking a look at a lamina. And if you're not familiar with what a lamina is, we're looking at a thin sheet of material. So let's suppose that a lamina occupies a region D. And that region D will be in the xy plane. Right? Density is going to be in mass per unit area. So once again, mass per unit area. Now the density is going to be given to us by some sort of function we're going to call rho of xy. So the density at a point xy is given by, once again, rho of xy. Rho is going to be a continuous function on this region D. So once again, rho is continuous on D. And the mass is going to be given to us by m, which is equal to the double integral over this region D of our density function, rho of xy. All right. So let's consider why this might be a reasonable way to represent the mass. Well, let's take a look at an example, or at least an illustration. You might have some sort of lamina, and maybe it's a parabolic region. Maybe you have a picture that looks something like this. There's some sort of density function, rho, that's going to be defined over this parabolic region. And so what we're going to want to do is get some sort of idea of what the mass of this lamina is. Now, one way to do this is to think about partitioning this region into subregions. So you might have a partition like so. And then over each one of these subregions, we're going to choose some sort of representative point. So maybe we're going to look at this subregion right here. So maybe that's the subregion we're going to be taking a look at. And suppose that what we want to do is consider some sort of point, some sort of representative point, and maybe that point is going to be xi star, yj star. Now, if we're interested in trying to figure out the mass of this lamina, what we're going to want to do is estimate the mass over each one of these subregions. And so you might say, well, how exactly is it that we would represent the mass? Well, remember, the way that the density is described here is in mass per unit area. So you think about density is in mass per unit area, then that means that the mass is going to be the same thing as the density times the area. So what we can do is we can plug this representative point, xi star, yj star, into our rho. So let's take a look at rho of xi star, yj star. Now that's going to give us a certain density, but we're going to assume that constant density over the entire subregion here. So once again, this will represent our constant density estimate over the entire subregion. Now, if you take that density and you multiply by the area, which would be some sort of delta xi times delta yj, let's say, then that would give you an estimate for the mass over that particular subregion. Well, as we've seen before, take a double summation of this as I ranges from 1 to n, j ranges from 1 to m. Take the limit as m and n both approach infinity, and what you're ending up with is a double integral of your density function. It's going to look just like this. Now, the same kind of argument can be made for solids in three-dimensional space, and a little bit later on in some of the other sections, we'll actually take a look at how that unfolds. But for right now, we're mainly interested in just laminas, and we'll leave it at that for the moment. Speaking of moments, really, I didn't mean to do that transition, but it just so happened. So the moment so let's see, what exactly is a moment? Well, the moment of the entire lamina about the x-axis So you might say, well, what exactly is the moment about the x-axis? Well, the moment is going to give us essentially a measure of the tendency of the lamina to rotate about the x-axis. So the way that we're defining this moment of the lamina about the x-axis is going to be by using this terminology. We'll have capital M sub x, and that's going to also be represented by a double integral. This will be the double integral over d. So remember, d is the region over which the lamina is lying. So we've got the double integral over d of y times the density function dA. So if you think about why is it, say a y times rho of xy, well, let's consider a situation in which maybe we have a lamina, and we'll keep this pretty basic, and maybe the lamina is occupying this region here. If you're looking at tendency for the lamina to rotate about the x-axis, then if you take a look at, well, let's think about maybe this is some sort of platform and we're looking straight down this platform. If you have, let's say, a couple of individuals, one standing right there and one standing right there, perhaps they're balancing each other out. Depending on how much they weigh, and depending on the density of the platform, they might be, maybe not exactly in these positions, but one thing we can say is that in this position, if this person were to move this way, then that would cause this lamina to move more in this direction. So a movement y-wise actually corresponds to greater tendency in this case to rotate about the x-axis. And if this person were to, let's say, move down or up, you would once again have this change in the tendency of the lamina to rotate about the x-axis. So we define this capital M sub x as the double integral over d of y times the density function. We're integrating that with respect to capital A. Now, the moment about the y-axis is going to be m capital M sub y. And as you might guess, this will be the double integral over d of x times your density function. So in the same manner, if you were to have, let's say, this individual moving this direction or that direction, then that would affect the tendency of the lamina to rotate about the y-axis. And that's what the capital M sub y is. It gives you some sort of measure of the tendency of the lamina to rotate about the y-axis, but x times the density function is what we're going to take the double integral of over this particular region D in order to get that measure. Now the center of mass is going to combine the ideas of these moments and the m that you see here. So center of mass is defined using this notation. We'll have x bar and y bar as the coordinates of that center of mass. And the x bar is going to be the same thing as this capital M sub y divided by little m. Whereas the y sub bar is going to be the same thing as capital M sub x over little m. So what I'm going to do is show you one example in which we have some sort of region described. We'll have a triangular lamina, as a matter of fact. We'll be given the vertices, we're going to find the mass, we're going to find the center of mass of this lamina. Now the mass, once again, is given to us by this formula. Center of mass, you have x bar defined that way, y bar defined that way, but we're going to need to know something about these moments of the lamina, about the x-axis and the y-axis. So let's jump into that example. Let's see what's involved. So the example we're going to be looking at is described as follows. Find the mass and center of mass and we're going to have this lamina that's triangular. Three vertices will be given to us. We're going to have one vertex at 0, 0, another one at 1, 0, and another at 0, 2. So once again, we're going to find the mass and the center of mass of this triangular lamina with the given vertices. If the density function is rho of xy is equal to 1 plus 3x plus y. All right. So once again, we have these given vertices that will enable us to see what our triangle looks like. In fact, let's go ahead and draw that. Notice we have one vertex at the origin, have another one at 1, 0, and another one at 0, 2. So our triangular region is going to look like that. Call it D. I'm going to describe this region as a type 1 region. So the bounds on x are going to be constant. Bounds on y, well, one of them will be constant, it turns out, in this particular case. But if we consider the x interval over which this region lies, we'll notice that it starts when x is 0, ends when x is 1. So the bounds for x will be 0 and 1. But then we have to consider what the bounds on y look like. We have a bottom boundary here, y equals 0. And we have a top boundary here, this line segment. So we have to come up with some sort of description for that line segment. Now notice that this line segment is going to intersect the y-axis at 0, 2. So we're going to have a y-intercept at 0, 2. And then the slope, you got a rise of -2 and a run of 1. Rise over run, -2 over 1. Okay, that's a -2 slope. So if you think about the slope is -2 and the graph is going to be intersecting the y-axis up here, then you're going to have y is equal to 2 minus 2x as the line upon which this segment is taken, or the line from which this segment is taken. So you've got this y equals 0 as your bottom boundary, and you have y is equal to 2 minus 2x as your top boundary. Now we're being asked to figure out the mass and the center of mass of this lamina. Remember, the mass is given to us by the double integral over d of rho of xy dA. Now, fortunately, we know all the pieces to put together to give us little m. And so on the outside, we'll go with our limits for x. And on the inside, we'll go for our limits on y. The rho of xy is 1 plus 3x plus y. And we'll integrate with respect to y on the inside and with respect to x on the outside. Now, having set this up, it's time to figure out where to go from here. And where to go from here is to integrate the 1 plus 3x plus y with respect to y. So we'll have m with the integral 0 to 1 on the outside, and then we'll integrate the 1 with respect to y. That'll give us y. 3x integrated with respect to y is 3xy, because remember, we're treating x as a constant when we integrate this with respect to y. And then the y is going to integrate to a half y squared. And we'll take that from 0 to 2 minus 2x. The 2 minus 2x will get plugged in for y, and then we'll subtract what we get when we plug in 0 for y. Alright, so mass is going to be the integral from 0 to 1. We'll plug the 2 minus 2x in for y here. We'll have a plus 3x times 2 minus 2x. And then we'll have a 1/2 2 minus 2x raised to the second power. And there's a bit of algebra, of course, that we're going to be expected to pull off here. So we have the 2 minus 2x. 3x times 2 gives us 6x. 3x times negative 2x is a negative 6x squared. And then we'll have a plus 1/2, and now we'll square this 2 minus 2x. Square your first term, gives you 4. Multiply the two terms together, it gives you a negative 4x. Double gives you a negative 8x. And then square the last term, gives you a positive 4x squared. Fortunately, we'll be able to multiply it through by 1/2, and it'll be pretty nice. So we'll have the integral 0 to 1. In fact, I'm going to go ahead and combine these. So we'll have a 2, and then the negative 2x plus 6x is going to give us a 4x. We'll have a minus 6x squared here. Let's go ahead and put the brackets around there. 1/2 times 4 is going to give us 2. The 1/2 times negative 8x gives us a negative 4x. And the 1/2 times 4x squared gives us a 2x squared. Well, this is pretty nice, because notice the 4x here and the negative 4x here are going to go away. So we'll have the negative 6x squared plus 2x squared gives us a negative 4x squared. Then the 2 plus 2 here will give us 4. And now we have something that's really easy to integrate with respect to x. So when we do this, we'll get m is going to be negative 4/3 times x cubed plus 4x. And we take this from x equals 0 to x equals 1. So when we plug in the 1 for x, notice we'll have a negative 4/3 plus 4. But 4 is the same thing as 12 over 3. So really what you have is negative 4/3 plus 12/3, and that's going to give you 8/3. So the mass is 8/3. You subtract what you get when you plug in 0 for x, but that's just going to give you 0 anyway, so we've settled upon an 8/3 as the mass. So at least the first part of this example is finished. But we still need to figure out the center of mass. We still need to therefore figure out the capital M sub x and the capital M sub y. Now, keep in mind that the x bar is the capital M sub y divided by m. And so one thing we could do here is we could say, let's just go ahead and take a look at x bar. So x bar would be the same thing as 1 over m times capital M sub y, which will be the double integral over d of x times rho of xy dA. Well, we've already taken the double integral over d of rho of xy. So if you really think about what it is that we're integrating here, we're going to have x bar is equal to 1 over m, and then we'll have the integral 0 to 1 on the outside, integral from 0 to 2 minus 2x on the inside. But then that x gets multiplied by the 1 plus 3x plus y, and that will give us x times 1 plus 3x plus y here. And of course we can multiply that through. Now, one other thing to consider here is that we're not going to have to keep writing this as 1 over m. We already know what m is. So if you think about what 1 over m is, you're just taking the reciprocal of this. So 3/8 will be the same thing as this 1 over m. We multiply through x times 1 plus 3x plus y. And what we see here is that we get x plus 3x squared plus xy. That'll get integrated with respect to y, and then whatever result we get from that will get integrated with respect to x. So integrating with respect to y, still have the 3x on the outside, integral 0 to 1, and now we'll have an xy plus 3x squared y plus 1/2 xy squared. We take that from 0 to 2 minus 2x. And now it's a matter of plugging in the 2 minus 2x and wherever we see y, and then subtracting what we get when we plug in 0 for y. And so that means we're going to have x bar is 3/8 times integral 0 to 1 x times 2 minus 2x plus 3x squared times 2 minus 2x plus 1/2 x times the square of 2 minus 2x dx. And we could say, let's go ahead and multiply all this through and see what happens. But there's a much nicer way to accomplish this. Let's compare what we see here to what we had here when we were figuring out what little m was. Think about the fact that the 2 minus 2x is now multiplied by x. The 3x times 2 minus 2x, because the 3x squared is multiplied by x. 1/2 times the square of 2 minus 2x multiplied by x. So instead of going through all this work again, what we can notice is that when all is said and done, this x bar is really just going to be 3/8 times the integral from 0 to 1 of x times this thing. So our x bar is 3/8 integral 0 to 1 of a negative 4x cubed plus 4x dx. So it saved a little bit of time with that, and that's pretty nice. That's pretty nice because the negative 4x cubed integrates well, so does the 4x. We'll have a representation for x bar. That'll be 3/8 times. Now we integrate the negative 4x cubed, gives us negative x to the 4th. Integrate the 4x, gives us 2x squared. Integrate that from 0 to 1. And now we plug in 1 for x, subtract what we get when we plug in 0 for x. And when we plug in the 1 for x, we get a negative 1 to the 4th, that's negative 1. Plus 2 times 1 squared is plus 2. Alright, so negative 1 plus 2 gives us 1. Subtract what you get when you plug in 0 for x, but that's just going to give you 0. So this x bar is really 3/8 times 1, which is the same thing as 3/8. So at this point we actually have our x-coordinate for that center of mass. Now we're also going to have to come up with the y-coordinate for the center of mass. But that's going to be our y bar, which is going to be the same thing as 1 over m times double integral over d of y times rho of xy. So let's make some room here, and we'll take a look at how that unfolds. So our y bar, once again, is 1 over m times double integral over d of y times rho of xy dA. So we're going to have y bar is the same thing as 1 over m. We'll have the integral 0 to 1 on the outside, 0 to 2 minus 2x on the inside, and then y times 1 plus 3x plus y dy and dx. Again, we know that 1 over m is the same thing as 3/8. That means that y bar is going to be 3/8 times. Once again, we have the 0 to 1 on the outside, 0 to 2 minus 2x on the inside, of the y plus 3xy plus y squared, dy dx. So we need to integrate with respect to y. And what that's going to do is it's going to give us 3/8 integral 0 to 1. We'll have a half y squared. We'll have a plus 3x times y squared over 2. That'll be a plus 3 halves xy squared. And then we'll have a plus integral of y squared. That'll be a plus 1/3 y cubed. We'll have to plug in 2 minus 2x for y, and then subtract what we get when we plug in 0 for y. Now, this is a bit of a mess. We know that plugging in 0 for y is just going to give us 0, but we had to plug in 2 minus 2x first anyway, and that's what we end up with. So here we'll get y bar is equal to 3/8 times integral from 0 to 1. And we'll have the 2 minus 2x raised to the second power. Once again, we saw this here. We get 4 minus 8x plus 4x squared, multiplied by the half as well. All right, so we'll write that down. But then we have the 3 halves times x times 2 minus 2x squared. So the 2 minus 2x raised to the second power, we already know is equal to this thing here. So we can multiply by x, and that'll give us, we'll have a 3 halves times, and then we'll have a 4x minus 8x squared plus 4x cubed. And then we'll have the 1/3 times the cube of 2 minus 2x. Now let's keep in mind what's going to happen when we take a look at the cube of 2 minus 2x. Well, we can use the binomial theorem here. And the first thing we can do is we can cube that first term. So 2 cubed gives us 8. After that, we'll have 2 raised to the second power, that'll give us 4, times negative 2x, times binomial coefficient of 3. So that'll give us a 3 times 4, 12, times negative 2x, gives us a negative 24x. With the next term, we also have a binomial coefficient of 3. Then we're going to have 2 raised to the first power. Negative 2x is going to get squared, so that'll give us a 4x squared. And that'll give us 6 times 4x squared is 24x squared. And then finally we'll cube that last term, negative 2x raised to the third power, negative 8x cubed. Now at this point, we've got a lot of stuff here to simplify. And we'll have our y bar is 3/8 integral from 0 to 1. Half times 4 gives us 2. And then we'll have a negative 4x and a 2x squared. And then we'll have the 3/2 times 4x, that'll give us 6x. And then we'll have the 3/2 times negative 8x squared, that'll give us a negative 12x squared. And then the 3/2 times 4x cubed gives us a 6x cubed. Finally, we expand this out, we'll have the 8/3 minus 8x plus 8x squared minus 8/3 x cubed. Now at this point we can start thinking about what sorts of powers of x we have. And we notice we have constants, x to the first, x to the second, x to the third terms. So what we're going to want to do is gather out whatever like terms we have. And as we move through this list of terms, we see that we have a 6x cubed and we have a negative 8x cubed. So we've got this here and we have this here. Now 6x cubed is the same thing as 18/3 x cubed. You subtract 8/3 x cubed from that, and we'll have this our next out. Y bar is 3/8 times integral 0 to 1. Combine these, you get 10/3 x cubed. We then take a look at our x squared terms. And the x squared terms, you have a 2x squared here, negative 12x squared there, and an 8x squared here. So you put those all together, it gives you a negative 2x squared. The x terms, you have a negative 4x, positive 6x, negative 8x. When you put those together, you're going to have a negative 6x. And then the remaining terms that are not highlighted, you have the 2 and you have the 8/3. Now, 2 is the same thing as 6/3. You add 8/3, you get 14/3. So this is looking way nicer than the previous steps. At this point, we're ready to integrate. We got our y bar, same thing as 3/8 times. Then the 10/3 x cubed is going to integrate to 10/3 times x to the 4th over 4. Now, 10/3 times x to the 4th over 4 is going to give us 10/12 x to the 4th, or 5/6 x to the 4th. The negative 2x squared integrates to a negative 2/3 x cubed. 6x integrates to a negative 3x squared. And then the 14/3 integrates to a 14/3 x. And yes, we're taking that from x equals 0 to x equals 1. We have to plug in 1 for x. And in the brackets here, we're going to get a 5/6 minus 2/3 minus 3 plus 14/3 when we do that. Subtract away when you plug what you get when you plug in 0 for x. Well, you're just going to be subtracting away 0 at that point. So we think about, well, if we have a 5/6 minus 2/3 minus 3 plus 14/3, what does that combine to give us? Well, the 5/6 minus 2/3, and that's going to be 5/6 minus 4/6 is 1/6. Then we'll have a 1/6 minus 3. That'll be a 1/6 minus 18/6, or a negative 17/6. And then when you take the negative 17/6 plus 14/3, that's a negative 17/6 plus 28/6, so 11/6. So y bar is going to be 3/8 times 11 over 6. And if you do the multiplication here, that means that y bar is 11 over 16. As a result, our center of mass is, well, we had what, 3/8 for x bar, and 11/16 for y bar. So we figured out the center of mass here. We had the mass of the lamina earlier, 8/3, and that finishes out everything that we were asked to do. Now, in terms of recommended exercises, I have these listed up here, number 3, 5, and 11.